Okay, let's keep where we left. So the next two lectures are probably the most interesting in that we will cover the main current results of neutrino astrophysics. I mean, the last two lectures have been mostly methodological in nature. But I have to speed up a little bit. About we have about 200 slides to go, so we will see how we can do about that. So I'm going to talk about backgrounds, more or less to give you a sense of what the backgrounds are here. I'm going to skip some of the equations just because I really want to get to the latter slides. So the problem of, oops, it works. When you have a very large underground detector, even though this detector is buried about 1.5 kilometers underneath essentially a mountain, which is the Antarctic glacier, you still get a lot of backgrounds from cosmics. And so here's a Monte Carlo of 10 milliseconds of ice cube data. Quote, this is simulation. And you can see here the different traces. They correspond to high energy muons that are producing cosmic ray air showers. So to give you a sense of scale, we are going to talk about 10 to 11 muons per year. That's about 3,000 per second. So this is 3 kilohertz rate that we were talking about earlier for the tree decision problem. About 1 every 6 minutes is going to be an atmospheric neutrino. So that's about 100,000 muons that are produced from neutrinos in the atmosphere. And then approximately 100 per year are actually going to be the ones that we care about. So that means that we have to do a background rejection of about 10 to the 9 on 9 orders of magnitudes. So how are we going to do that? So what is this background? So I will not talk much about this, but it's produced by cosmic ray hitting the Earth atmosphere. Let's see. Oops. So when you have cosmic rays, they hit the Earth atmosphere, they produce hadrons. These hadrons are going to decay. In this decay, they're going to produce muons. There are going to also be production of neutrinos. So there are going to be two main backgrounds, neutrinos, which are to some extent irreducible backgrounds, and then muons that are going to be reducible in some directions of the detector. Okay, what happened here? So the production of atmospheric neutrinos is going to come from the decay of these mesons. Predominantly, it's going to be from muon decay. So that's going to produce equal fractions of mu e and mu mus. You're going to have pion decay, which is going to produce exclusively, essentially, muon neutrinos. And then you're going to have kaons that are going to decay into a combination of muon neutrinos and electron neutrinos. So you see that most of the time you get muon neutrinos from the kaons, but there is an electron neutrino component. And remember that for us, there is a correspondence between muon neutrinos and track-like morphologies and electron neutrinos and cascade-like morphologies. So this component here is going to end up in a different morphological category than, say, this background here. So we're going to talk about two important components. There is the conventional atmospheric neutrino component that is produced by protons or heavy nuclei hitting air that makes pions and kaons, k short, k long. And that's how this decays. And that's going to, as I mentioned, produce muon neutrinos. And then from the kaons, you're going to produce these electron neutrinos. We call this conventional component because this has been measured now over many decades, so this is actually fairly well understood. Okay, let's see. Then there is also a second component that we call prompt components, and we'll see why that is in a minute. But we call them prompts because when these mesons are produced from proton or heavy nuclei air interactions, they produce heavy quarks that contain charm contents. For example, D or a lambda C. And these heavy quarks, they tend to decay in 3-body processes, like that. And they're going to produce a high energy component of atmospheric neutrinos. However, this is a subdominant component. So most of the background is this type here. In fact, so far, we have not been able to measure neutrinos produced from the meson decay. Okay. So this is a huge equation. And what this equation tells you, it tells you the way atmospheric neutrinos are produced in the atmosphere. So this is sort of the master equation. There is population of hadrons at some height in the atmosphere. So here x is the height measured in column density. And then phi h is the flux of a given hadron. And so what you have to do is to compute the chances that a given hadron interacts in the air. This is this. The probability that the hadron decays in the air, which is given by this term here. These hadrons, when they go through the air, like pions and kaons, when they are actually going through the atmosphere, they're going to lose energy. So you have to model those energy losses. And then when those hadrons interact with the medium, they're actually also going to produce lighter hadrons. So you have this sort of cascading equation. So you can solve this numerically. And there are several elements that enter here. There is cosmic ray physics that tells you the initial population of hadrons. So this tells you the hadrons that start in the beginning of the shower. There is atmospheric physics that tells you the medium in which this shower is developing. And that's actually measured by satellites. So satellites are constantly looking at the Earth atmosphere, measuring pressure and temperature, and from that you can extrapolate and figure out the density. And then there is particle physics that tells you that when a given hadron actually hits an air molecule in the atmosphere, what actually happens to the hadron depends on particle physics. So there are uncertainties that actually come from all these three origins. There are actually two different regimes. So here you have the energy in the laboratory frame of the meson, and then here is the decay length of a given particle. So when you are below this line, so that, you are actually dominated by decay. That means that, for example, if you have a d meson of 10 to the 4th, that d meson will essentially decay instantaneously. Whereas when you are above the line, you are actually dominated by interactions. That means that if I have a 10 to the 4, for example, kaon, the 10 to the 4 kaon will leave enough distance that they will actually lose energy as it travels through the atmosphere before it decays. Whereas if I have a sub-100 GeV kaon or pion, that will essentially decay on a spot. Okay, so we have these two regimes. And that's important because that means that at high energies, the spectrum of neutrinos produced from pions and kaon decays is softer than the spectrum of the cosmic rays because they are losing energy in the atmosphere. On the other hand, d mesons, they essentially always decay before they actually are able to interact, which implies that neutrinos from d meson decay are always going to be more energetic than neutrinos from kaon and pion decay. Now, what's the relationship between a neutrino and the nucleon? So here you have different energies of neutrinos and different flavors. This is a muon, this is nu mu, and nu e. And here you have the corresponding cosmic ray energy that produces that. So when I'm talking about, let's say, 1 TeV neutrino, okay, so this is this light blue line, I'm talking that is typically produced by neutrinos of a factor of 3 or 4 higher energy. So there is, but this distribution, note that they're quite broad. This is a linear scale in the y-axis. So a factor of between, let's say, 3 and 5 is where most of them parent particles or parent cosmic rays are with respect to a neutrino. And so these distributions essentially depend in particle physics. And so the problem is that these distributions are actually need to be measured in laboratory experiments. And so at the lower proton energies, they can be measured in fixed target experiments. So this top axis here tells you the center of mass energy of nucleon-nucleon scattering. So for these sort of energies, this has been measured in fixed target. This sort of energy has been measured in the Tevatron, which was an accelerator of Fermilab in the 90s to 2010. And then this has been measured in the LHC. So essentially, we have good coverage over most of the energy range. However, most of these detectors, these two in particular, look for collisions that are central collisions, so they are not along the beam pipe, but actually go orthogonal to the beam. So there is some kinematic difference between these and these cosmic rays that are relevant here. Oops. Okay, so this is the plot that I really want to focus on. In particular, the one on the, well, let's talk about both of these. So this is the flux of muons, and this is the flux of muon neutrinos. So the flux of muons is essentially always dominated by pion decay. Okay, so pion goes through a two-body process where it decays into a muon and a muon neutrino. Whereas the flux of muon neutrinos is at lower energies dominated by neutrinos from pion decay, and at higher energies dominated by neutrinos from kaon decay. So why is it that the muons are always dominated by the pion? This is just kinematics. When you have a two-body decay, most of the energy always goes to the particle that has most mass. Okay? So this is just because when the pion decays to a muon plus a neutrino, just because of kinematics, the muon will always get more energy than the neutrino. And you can prove that yourself. And so the muons that we are concerned about are mostly from the pion components. But the neutrinos that we are concerned about, remember where we're talking about TV or sources, are actually going to be from kaon decay. This is actually quite important because you could say, okay, you have a background, backgrounds are annoying, that's a problem. So you want to remove them, just measure the muons and then subtract the muon neutrinos. That doesn't work because the muons actually come from pions, whereas the muon neutrinos come from a different process. So they're only weakly related. By the way, these calculations that I'm showing you can be done with a software called MCQ, which stands for Matrix Cascade Equation Solver. And it computes this with like up to the processes. Then it's also electron neutrinos. So this is the electron neutrino flux. Just to compare, remember that this axis is at the 10 to the minus 1 level. This is at 10 to the minus 2 level. So the electron neutrino component is smaller. The electron neutrinos at the very low energies are produced mostly from muon decay. And then there is a population that essentially comes from kaon decays. So the electron neutrinos and the muon neutrinos are actually coming from correlated particles. They're both coming from chaos, though slightly different kaon pieces. Now, there is this blue population here. This blue population here is the population from D meson decays. These are very heavy, say, mesons made of charm, that has charm contents that are going to dominate somewhere above like 100 TeVs. In the case of the electron neutrino components, we see that the electron neutrino flux is actually dominated by the D meson somewhere around 10 TeVs. Okay, and just so you know, this D meson contribution has a factor of 5 error in this normalization, so it can go up or down by a factor of 5 easily here. Okay, so one thing that you could do is try to look as a function of direction. So one thing that we discussed in the last lectures is that muons, if you have a high energy muons, they can only go at best tens of kilometers, which means that if I look through the Earth, there is no way that muons are actually going to go to the planet. And so for that, I just want to remind people of our zenith angle definition. So the zenith angle is defined so that the cos theta of -1 is equal to, is in this red arrow direction, and cos theta of 1 is in this upgoing direction. Okay? And cos theta of 0 is horizontal. So when I look at the rates of muons in a detector like Ice Cube, you see that in this downward going direction, we call it downward going because if you were to stand up where Ice Cube is, this would be falling downwards towards us. You have a very large rate of muons. However, when you look at events in this direction, your background is essentially going to be atmospheric dominated. And these are very different, right? So there's a factor of 1 million between this and that. So that's going to be important because if I want to find astrophysical neutrinos, it's much easier to find them in this direction than in this direction, right? Yes. Yeah. Yeah, I'm going to repeat your questions just so everybody hears it. So the question was, in these figures here, is it the flux in a particular direction or what direction and in what location? So these are, I think, average over direction. And these are at the sort of surface of the Earth. We'll talk about oscillations later. We haven't talked about that yet, but we will talk about that. And so oscillations are going to be important somewhere below 100 GeVs. Okay? Good. Okay. Okay, so that's all I want to say about the backgrounds. I just want to say you that there are two backgrounds that are a problem. One is atmospheric downward going atmospheric muons, huge, very bad. And there's atmospheric neutrinos, also pretty bad, but okay, it's a million times easier. So pick your problem you want to face. Okay, so now let's try to figure out how to solve it. So this is a two-pronged assault into this situation. So how are we going to find astrophysical neutrinos? Because we have to find essentially 1 every 100 million muons will be one of astrophysical neutrino events. So there are two ways you can do this. So the difficulty is, well, this is energy. This is flux scaled by energy squared. This is a typical level of astrophysical neutrinos. This is atmospheric neutrino background. And remember that above this, there is a million times higher, right? So we need to figure out how to overcome these large backgrounds and this very, very tiny flux. And here is our detector. This is, by the way, this is exactly the same if you were to be in any point of the Earth, because this is actually, symmetric. Or rather, let me say this in another way. To first order, the cosmic rays are impacting isotrophically over the surface of the planet, right? So in every point in the planet is about the same. Okay. So one solution is, well, let's look here. If we look through the planets, you are reduced to only the neutrinos produced by the muons that are produced by neutrinos. So you can do that. So strategy number one is look at the northern hemisphere, or if you are, say here, look in the direction of the planet. So if you look in the direction of the planet, now suddenly all of those 10 to the 9 muons per year are gone. And now I only need to care about the neutrinos. So it so happens that we actually understand fairly well how the atmospheric neutrino component should behave, because we have measured the cosmic ray components, and we know how pions behave in the atmosphere. So this, there is a red line behind this purple line. You cannot see it because it's exactly on top of it. But this is the component produced by conventional atmospheric neutrinos, right? So you see it has this slope. And so it follows with a slope of about almost e to the minus 4 in flux, so this is in rate. And you can see that at high energies, what you're looking for is some kind of deviation from this slope. So you're looking for a kink structure here. So the idea is that astrophysical neutrinos are harder than this atmospheric neutrino Falling spectra. And so I'm looking for a deviation in the behavior of this red line. So you can see that somewhere around tens of TeVs, the data points start becoming larger than the prediction of the atmospheric neutrino background. And so you will tell me, like, how do you know this background cannot go up? Well, the reason is that if the background goes up, all of these points have to also go up. So they're very correlated, right? So all of this data here is actually constraining how this tail moves down. Oops, oh, what happened? That was interesting. Okay. So we have actually done this. This is shown for 8 years. We have now 10 years of data, but to first order, this is the same. So this is seen for several ice cube years, and you can see that in every year, compared to the blue is atmospheric background. You see that at high energies, every single year, there is an excess of events over that conventional background. So what you can do is you can try to fit a power law that represents an astrophysical neutrino component, and you will get that that power law is something like e to the minus 2.2. This is depending on the data sets and how we do this event selection. So this is the way you can find astrophysical neutrinos to begin with. So now let's talk about strategy number 2. Strategy number 2 is, okay, so strategy number 1 is nice because I can look at all of this direction. I remove all of these nasty muons. But that means that I cannot look in this direction. And why is it important to look in this direction? Because you want to have all sky coverage. And in particular, the galactic center for ice cube is in the southern hemisphere, which means that with the other technique, we cannot see it in an effective fashion. So what you could do is you say, okay, I'm just going to introduce a veto region so that I fiducialize my detector. This is my detector. And I decide that I'm going to keep events that only start within my detector instrumented volume. So for example, this outer layer is my veto, and if an event is going through, and these blue dots imply that they are seeing some light in those photosensors, this is most likely a muon. However, this is most likely a neutrino. Okay? So you can define that, and the advantage is that you have acquired all sky vision. The disadvantage is that you have lost 1/3 of your detector, because all of this region outside is just now used to reject background. So your effective area is going to be smaller. So this is actually the way astrophysical neutrinos were first discovered, about almost exactly 10 years ago, in fact. So this is, I think, a very beautiful plot. Let me spend a couple of minutes on it. Yeah? So you could also use, so I want to repeat Orlando's question. So he's asking, why don't you look for events that do not exit your detector? Because we're saying that muons, high energy muons, always go 10 kilometers or so, so you know that it cannot be a muon if it's inside my detector. The answer is that also works. So that means that if I select for only cascades, and the cascades are not in the border, that's fine. There is a dangerous part about this. And let me draw why that's not as simple as it seems. So imagine that you have a neutrino, comes in like that, and it interacts here. Okay, so it makes a splash of light, right? So there is a DOMS hit here. But now this could have been a new E, right? And then I'm happy this is a neutrino. But this could also have been muon neutrino, right? Where this muon is going out. Okay, and sometimes muons, remember that muon losses are stochastic, which means that there is a chance that a muon goes through some many meters and thus essentially loses no energy. Okay, so the dangerous part about doing that, and we'll talk about it a little bit more, is that you can have these things that are coming out. Of course, you still gain because clearly this background is not a muon, but it is still an atmospheric neutrino in principle. That's a great question. By the way, but you can deal with this, and we have also measured it with cascades only. So this also works, but it's just harder. These are the easiest two methods, let's say. Okay, so in this figure here, you have, these are three-dimensional histograms, which is always very confusing. So let me just spend a couple of minutes on it. So this is the amount of charge that is in the outer layer of my detector, measuring photoelectrons. And this is the amount of charge that an event deposits within the detector fiducial volume. Okay, and so the height of this is the number of counts. So this is the number of counts per so many days. And this bin here, don't worry about it. This is just an overflow bin. That's just, this histogram essentially continues, but we have cut it off there. And so you can see that there are all of these events that deposit large charge in my outer veto and have a distribution of energies. And then there are these events here, in this line here that sticks out. These are events that deposit no more than 3 photons in my outer layers of my detector. However, they deposit, tens of thousands of photons inside of my detector. Okay, so those are the ones that we are looking for. And you can see that pictorically, this component is very different than these huge backgrounds. And so those are actually going to be our astrophysical neutrinos. So the first ones were named after Muppets. They were Bert, Ernie, and Big Bird. They were seen, like I mentioned, about 10 or 11 years ago. And if you look at them for too long, they will actually start looking like their characters, but maybe it's too many years looking at these little diagrams. Now we actually have a lot of them. Okay. We also have, remember, I mentioned this very briefly, that we have iStop, which is on top of the IceCube observatory. So this is an event, right, that interacted in our detector, somewhere over here, and is going downwards. And the most likely direction of this neutrino is this direction. And you can see that essentially there are no on-time hits in this color. Remember that color means time. Essentially, there are no yellow color hits in this top region, right? So we know that this, for example, for sure must be a neutrino of astrophysical origin. Unfortunately, this only works for a tiny sliver of space, so that's really unfortunate. I mean, if we could cover all of the Antarctica with sensors, that would be great, but we cannot do that. It's too expensive. Okay, oops. So the question is, well, we have these events. These are, we call them HESI, for high energy starting events. We call them starting events because they start inside the detector fiduciary volume. So this is a famous acronym now. And this is those events shown as a function of direction, declination now. And then this is the energy deposited within our detectors in TeVs. So these points here, these ones here, these are PEV events. And these ones are for sure astrophysical. There is no way you can produce these events with atmospheric neutrinos. And so the question, and then there are these events here, right? This chunk of events here. The question is, how do we know that most of these events are also astrophysical? Because in principle, we could have a situation where, like I was mentioning earlier, it could be an electron neutrino interacting within my detector. Namely, we're concerned about that maybe these events are things like, I'm actually going to talk about it in the next slide, I think. So I will draw it in a minute. So another thing that's important is to know that this is the northern hemisphere and southern hemisphere. So to realize if these events are astrophysical or not, we're actually going to use this directional information, right? So we're going to take advantage of not only the energy component, but the directional component to figure out how many of these are astrophysical in nature. So this is the expected angular distribution of backgrounds. So this is the shape of the conventional mu neutrino component as a function of direction. This is the shape of the electron neutrino component as a function of direction. And this is the shape of the production of prompt component, which is produced from the meson decays. And they're shown from these different directions. So you see that the atmospheric neutrino background is maximal at the horizon, and then it sort of falls down. Okay. So the question is, how can I be sure that most of my neutrinos are not this atmospheric neutrino background? So how do we open, how are we able to look in this sort of downward going direction? Okay, so what's the concern? The concern is, here is ice cube, here is the atmosphere. This is my inner part. This we call the Vito region. Okay, so suppose that you have, a kaon is produced here in a cosmic ray shower, and this kaon decays, and it makes a new E, and this new E is there. Okay, so this is not an astrophysical neutrino, right? It's produced by a kaon decay. So the question is, how do I know that most of my neutrinos that start in the detector should be of astrophysical origin, and they are not actually electron neutrinos produced by kaon decay? And in particular, this is actually more dangerous in the downward going direction. So this was actually figured out in 2009 by these authors here, and it comes out with a really clever idea. And the idea is the following. So suppose that I'm actually going to make this a little easier to begin with. Okay. Suppose that there's a cosmic ray that comes like this, and this starts a cosmic ray shower. And then here we produce a pion, and then this pion makes a mu neutrino. And then this mu neutrino interacts here, and it makes a muon. So this passes my selection, so I keep this event. This is a good one. But this one is still an atmospheric neutrino. It's produced by some pion decay. But then you will say, well, but we know that pions decay, essentially always with a muon and a muon neutrino. So this diagram cannot be correct, right? Because what happened with the other muon? So there must be a muon here in this process. That. Okay. So that means that my requirement of rejecting events that have charge in this region is not only rejecting single muons that are coming by themselves, but it's also rejecting possibly the cases of this muon neutrino coming alone. Now, let's go to a more complicated case. I'm going to make my Earth very small, so sorry because I have a small space. So now let's say that we do another example. So let's say that we do kaon is produced here, so I start a cosmic ray shower. So proton comes here, and then a cosmic ray shower happens, and there's a kaon is produced here, and this kaon produces now an electron neutrino. Okay, now this hits here, and I see a blob. Okay, so I keep that one too. But now that electron neutrino must be accompanied by at least one electron here. But now you will tell me, okay, what happens with that electron? Well, electrons, once they hit the Earth, they are dead. You know, they are not going to go more than order meters. So that electron will not reach you. However, this electron neutrino is a high energy neutrino, which means that this kaon must also be a very high energy particle, which means that this cosmic ray here must also be a very high energy particle. So when I have a very high energy proton that hits air, there is no way essentially that only produces a single kaon and nothing else happens. This is not how particle physics usually work. So most likely there are other things bundled up in this shower here. Okay? Most likely there is also here some pions being produced in this hadronic shower. And some of those pions could in principle decay, making muons. So the trick is that if we understand the production of mesons in these cosmic ray showers, we understand how likely is it that you get a neutrino of some energy without an accompanying muon. So what you need to do is answer the question, given that I saw a neutrino of energy greater than some value, what's the probability that it had no sibling muons? Okay? So how likely is it that this happens? So you can answer this question in multiple ways. One way is you can brute force it via simulation. You can throw many cosmic ray showers, and you can do that and figure it out. And so the answer is that this is actually quite unlikely. That most of the times when you have a high energy neutrino produced, you will also have somewhere in that shower a high energy muons. Which means that by rejecting events that interact, by selecting events, that interact inside of my detector, not only am I selecting for neutrinos, but I'm selecting for neutrinos that, at least in the downward going direction, must be astrophysical in nature. Okay? Is that clear for people? This is a little subtle argument, so I wonder if people have questions on this. So my statement is, if I select for neutrinos that interact inside of the inner part of my detector, and I select the high energy ones, I am essentially guaranteeing that most of the ones that are coming downwards have to be astrophysical. Because if not, there should be most likely a correlated sibling muon somewhere in my shower. So this is an argument that is complicated, because if some of you remember, like in the first lecture, when I was showing you the Amanda Observatory, when people had a penguin looking through the Earth, right? So since the beginning of neutrino astronomy, people always thought that the way to find astrophysical neutrino is to look through the Earth. This is the best way because you cancel the muons and you only have muon neutrinos. But it turns out that because of this correlated muon physics, it's actually much more efficient to see it in this way than in the other direction. But notice that this was realized in 2009, and the neutrino telescope idea was proposed in 2000 in the 70s. So this was 40 years later, right? So this is, now it sounds obvious, but it wasn't so obvious for many decades. And why it's not so obvious is because this is actually quite difficult to compute. This is very complicated hadronic physics that you have to simulate. But is this argument clear for everybody? So this is the argument that actually led to the discovery of high-energy astrophysical neutrinos 10 years ago, essentially. Yes? Yes, yes. So this is the difficult part because it's not only that you have to know how many muons reach, you have to know very well what the chance that the muon loses energy here. So you need to understand your probability that the muon, we call them dark muons, that there is no dark muon that accidentally crosses. And that's going to be a background. So you're right, that's a problem. And so the tighter your detectors are, the more efficient this outer veto is. If your outer veto is very porous, this doesn't work anymore, and you have a problem, okay? And so you need to understand both the cosmic ray physics and both, like Orlando is saying, the efficiency of being able to reject that this muon actually went through his. Yes? So your question is, what do we use to simulate this? Mm-hmm. Yeah, so that's very difficult, essentially. And the issue is, it's very hard to predict the muon multiplicity. It's much easier to predict the highest energy muon produced, which is not exactly the same. When cosmic ray people look at horizontal muons, they're looking at muon multiplicities and muons sneaking in. What we care about is the most high energy muon that passes this through. And so, but you know, when I talked to Francis Halsen, who is the PI of IceCube, you know, his biggest fear for many years, and now he doesn't have any fear anymore, but was that that was actually wrong, that the calculations of muon was incorrect, and that the muons were sneaking in. This is the nightmare scenario. But now, as I will show you later, we have found astrophysical neutrinos in many, many ways, so this is not a concern. But for at least, I want to say, the first 7 years, it was certainly the most dangerous point, because this is not clean physics. This is very dirty physics. And I will show you that you can compute this, how difficult this is to compute, in a minute. Yes, you had a question? Somebody had a question, no? Cool. Okay, questions on this? How am I doing on time? Yes. Yes. Yeah, so the muons typically come in bundles, right? So they come, many of them at a time. So that is sort of trickier to simulate. And what we do is we compute this sort of rejection efficiency, assuming a single muon, and then we verify for some directions that the full simulations have all of the muons give you approximately the same rejection efficiency. And that seems to work fairly well. But this is something that you cannot account in an easy fashion. Good. You guys are asking all of the good questions. Good. Okay. So I'm just going to very quickly tell you why this is a little of a nightmare. So there is something known as the passing fraction. And so the passing fraction is the probability that an accompanying muon passes everything, you know, that it sneaks in through everything and just interacts in your detector. So this is what you want to estimate. And this is going to depend on the cosmic ray flux, it's going to depend on the shower development, it's going to depend on the muon energy losses, and it's going to detect in your detector efficiency of response. And so you have to compute this, and I'm just going to skip most of this, but the cosmic ray flux, like some of you mentioned, has big errors. Composition is unknown, spectra is to some extent unknown. Shower development has hadronic uncertainty errors, also very tough to compute. Energy losses, actually not so bad. This we actually understand fairly well. Muon energy losses are understood to be about 3% in this energy range. That's okay. And then the detector response, this is sort of Orlando's question. You really want to simulate what's the probability that the muon is dark here, right? And so that's the detector efficiency is now within 10%, so we can figure that out more or less pretty well too. And you have to put everything together. I'm going to skip this because it's a complicated calculation. But you can look at the slides later. And if you want to compute this, you can actually compute it with this code here. And so then when you do that, when you consider the fact that you have this suppression factor, you end up with these solid lines. So the dashed line is the original background, and the solid line is the background when you have no accompanying muon. Okay? So for the direction that is the northern hemisphere, so the upgoing is exactly the same, because the muons never reach to you, so there's nothing you can do. But for the southern hemisphere, now this is suppressed. Okay? And now the important part is that now you look at the directional distribution of your data. And you can see that the distribution of astrophysical neutrinos, of neutrinos, that interact in your detector as a function of direction in high energy is actually flat. Whereas the background is actually suppressed in this direction. So there is no way that this thing can go up by a factor of essentially 200. Okay? And so this is the reason that we know that most of these neutrinos have to be astrophysical in nature. And this plot essentially is what convinces us that we're actually seeing astrophysical neutrinos. Are there any questions on this? Yes. I think there's a mic here.
Okay. So I think that maybe the size of your veto region, the outer veto region, affects the efficiency of your methodology. No?
Mm-hmm.
My question is like, is there like an optimal number, an optimal size of your veto region?
Yeah.
Because I think you lose quite a volume by doing this veto region, but I understand why you do that. So is there like a optimal number?
Yeah, that's a real question. So the question is essentially, how do I decide on my veto region size? Yeah. So if this is my detector, and I want to detect very high energy neutrino, okay, that means that the accompanying muon is probably also very high energy. So that means that I can try to optimize, given that I more or less can figure out this muon energy, I can pick a veto region that is kind of thin. But if now I have a lower energy, I need to actually thicken this layer wider. So what we do actually is, given the energy that within the neutrino has, we optimize the veto region to more or less have a good signal to background purity. And this is done dynamically on the amount of charge that you have in your detector. So we do it, we know how much energy is deposited inside. And let's say that for this outer region, it's like, let's say, 10,000 photoelectrons. For that, we know more or less the energy. We say we put one layer of sensors. And if it's, let's say, I don't know, 1,000 photoelectrons, then we put maybe 3 layers of sensors. Okay? We also put more sensors like in the top. Like we put like only a little bit in the bottom, right, or nothing. So we optimize on this. This is not easy. Like doing that optimization is a whole PhD thesis. So this is not a trivial thing. Good. Great. Okay, So when you do that, you measure the neutrinos. So this is the energy distribution of neutrinos. Okay. This is astrophysical neutrino. This is data, and this is expectation. And you can see that most of them are astrophysical in nature. And then this is the unfolded flux. But I want you to notice something I think interesting is that the spectral index that you get here is very different. It's like e to the 2.9. And so this was a problem because people that actually work in cosmic rays know that the cosmic ray is spectral like e to the 2.7. And so this is dangerously close to that number. So this was concerning at the time. And more importantly, it's different than what we see for the northern hemisphere. So there was some slight tension between them two. Okay. So now we've actually measured the astrophysical neutrino flux in multiple ways. So this is sort of a first summary plot. In all of these measurements, let me explain you what this plot means. This is, we assume that the astrophysical neutrino flux is given by a power law that's unbroken. So it's something like e to the minus gamma. And then this is the normalization of that flux per flavor at 100 TeVs. And so here in yellow is the measurement using the starting events. This is the first measurement that was done. In blue, this is one of our latest measurements using true-going events. Then in green, this is what Orlando was asking earlier, which is just select things that are round in your detector. You know those are not muons. You can also do that. That gives you this answer. And then you can also look for muon neutrinos that start in your detector, and you can measure the hadronic and muon energy, so you get this answer. So you see that this sort of cluster around e to the 2.5. But each of these ways of looking for astrophysical neutrinos have different flavor dependence. They have also different energy ranges that are sensitive to. So the fact that these differ a little bit is not surprising, because most likely astrophysical flux has some kind of shape, and each of these pieces is sort of looking at a different piece of the spectrum. Okay. I also want to highlight here that there is another contour for Antares, which I think this is only the best fit point appears here. But the contour of Antares has a very large error. Okay. By the way, Orlando's point about using the showers was actually proposed by John Beacon, who's a theorist at Ohio State, in this paper called the power of showers, or shower, I think it was called shower power. And you can look at that reference where he points out that you can actually do it. So a really nice read. Okay, so there are two complementary ways to discover and measure astrophysical neutrinos. There is the cascades, and on those you can get all flavor, all sky by using this Vito technique. You can measure the energy, so essentially calorimetrically. And then you can use also muon neutrinos, which you can go to the northern hemisphere. Those are superior angular resolution, but as we discussed, because the muon losses are stochastic, the end resolution is not good. Okay. So here is another way of looking at this information. Here is the neutrino energy. Okay. This is the flux normalization at 100 TeVs. Oh, sorry, the flux normalization at a given bin. And so you can see the different events here. This is the muons. This is the starting events, are these crosses. Okay. So the reason the starting events give you an e to the 2.9 is because when you connect this point with this point, you get a slope that is steeper, kind of like that. We will talk about this Glasgow event later, but don't worry about it for so much. But you can see that there is sort of an excess of events compared to the muons slope. And so what we're currently thinking is that there is maybe a more complicated shape that could be maybe something like curves or whatnot that describe this data. Okay. This is another way of looking at it. This is the muon neutrinos, and this is now a more recent analysis that looks for cascades, and you can measure it like that, and you can see that again this is strictly higher than the muon neutrino case. Okay. So that's what I want to say about astrophysical neutrino diffuse measurements. That's the sort of all-sky integrated measurements. And now I want to talk about neutrino sources in the next. I started at 2:30 or at 3? 2:30, right? So I have 30 minutes. Oh, okay, good. Okay, we'll get there. Yeah. So let's talk about neutrino sources a little bit here. So this is if I take all of my neutrino candidates that I select in 1 year of IceCube, this is how they will look in 1 year. If we put now 10 years, this will be essentially all blue. So that's why I picked the 1 year's point. This is in galactic coordinates, so the galactic center is sort of in the center here. And remember that we are talking about 120 astrophysical neutrinos over in this box. So another thing that you can do is maybe obvious, but if there's a astrophysical neutrino source, you just look for clustering around a point, right? So I don't care about backgrounds or anything. Just look for a cluster, and that should be astrophysical neutrinos in nature. So that's what we are going to talk about. We're looking for cluster positions. So these are the highest energies of those events. Here, the color scale represents the energy of the neutrino. And now here I actually label the through-going tracks, which is open circle, and then these are actually the starting events. Okay. And so you can see that they are sort of split evenly through the sky, though of course the northern tracks are only in the northern, you have the phase space. So there are 3 important neutrino hotspots in the sky. These are NGC 1068, TXX 0506, and PKS 1424. And so the brightest of this one is actually NGC 1068. And that actually was recently announced to be a neutrino source, which was published in Science last year. And so this is the number of neutrino events that we see from NGC 1068. This is a function of the separation from the source position in degrees squared. So you can see this is the background, which you can get from extrapolating the data, or off-source data. And then here is the X of events. So this is more than 4 sigma detection probability. And so here you can see the flux of this source. I'll talk about TXS later. But this is the astrophysical diffuse spectra. That's what I was talking to you earlier. This is the all-sky neutrino emission. And this is the flux from NGC 1068, and this is the flux from TXS. So we are able to observe these diffuse neutrinos from extragalactic sources. I'm going to talk about the galactic component later today. But we are still looking for these sort of correlated pegatron sources. Okay. So I want to go back to this slide, which I showed in, I think, my first lecture, which is to think about the relationship that there should be between neutrinos and high-energy gamma rays. If you remember, the idea is that you have some kind of cosmic accelerator that accelerates protons. Those protons hit some target that could be dust or radiation, and those produce pions. And those pions then decay, making neutrinos if it's charged pions, or making gammas if it's neutral pions. So then you expect some kind of correlation between these two messengers. As we discussed earlier, the gamma rays get absorbed in the trajectory, so that's why you want to use neutrinos. And these gamma rays, however, do not just disappear. They are not just eaten up into space. They start electromagnetic cascades, so they're going to loop down to lower energies. And Armani is going to talk about that much more than me, so I'm just going to go through this fast. And so what you can do is you can assume that the astrophysical flux follows a power law given by this black line. And then you can compute, if you assume that there are equal amounts of pi zeros neutral pions, and you assume that your sources are transparent to those pions, then you can compute the expected gamma rays that you should observe. And so that gives you this red line here. So you see that this works fairly well, except for the problem that this doesn't work for the neutrinos, because there is this data point here that's quite high. And this is related to our cascade measurements I was talking to you earlier. Okay, so what happens if I, instead of doing this fit, I do a fit that goes kind of like that? So if you do that, if you do a fit that now follows this data point here, you actually get a software spectrum. And that's associated to a software spectrum also in the gammas, and you get this line in red that now overshoots all of these gamma ray measurements. So the observation of neutrinos at a relatively high flux on the tens of TeV energy range indicates or suggests that the sources of astrophysical neutrinos may be dark in gamma rays, right? So maybe we are seeing something that is an intrinsic opacity of the sources in gamma rays. I'm going to see. So this is sort of like another way to look at this sort of excess of low energy neutrinos that is contributing to this excess. So if we think about the spectral index as a measure of this sort of steepness, in which case this will start becoming a problem with gamma ray measurements, essentially things that are harder to about 2.2 in the spectral index tend to produce spectra that starts to be in tension with the gamma ray measurements, as long as you imply that the sources are gamma ray transparent. Note that this also assumes that the flux is entirely unbroken up to lower infinity. If it curves, this of course changes, right? Okay. Okay. So what's going on here? I'm going to skip this because I want to talk about multi-messenger. So one thing that we have been doing in SCube to find these astrophysical sources and try to figure out this puzzle is to look for gamma opaque sources in correlation with other messengers. So the idea is that you have some source, and that source emits, let's say, gammas and neutrinos, and you have observation of a gamma ray in, let's say, Fermi. And then what we can do is we can see if we have actually a coincident observation of high neutrino at the same time. And this is nice because this is sort of testing this intuition that we're getting from the diffuse flux that maybe there is actually something more complicated going on in this picture. So we have an IceCube alert system that is public. So for example, this is one of our astronomer telegraphs that shows you the energy of the event and the most likely direction that that event has. And this connects to what I was talking yesterday, that it's important to have a real-time system that promptly reconstructs the neutrino event so that our partners in other observatories point in the directions of our neutrinos. Unfortunately, the reconstructions that we can do in the South Pole right now are actually quite rough. So we do is we put out a first alert with the first thing we have, and then over the next hours, we try to improve them. Remember that, at least with traditional reconstruction methods, reconstructing an event like this can take several hours. So this is ideally how it should work with our first reconstruction. So here is the IceCube domes. They go to our data acquisition system. There is approximately 5 seconds that our trigger takes. Then we have to do some filters, select if this is cascade, track, what exactly are we looking at. That's about 20 seconds. That then goes to a messaging system, and it goes through satellites to UW-Madison in Wisconsin, about 20 more seconds. And then we send up as a follow-up server. So the whole process takes order of minutes for our first reconstructions. So we're trying to get these things faster. Like I was mentioning earlier, this is actually going to be harder, but making this go fast is something that at least I'm trying to do with machine learning. So this system here had some rather successful events, and I'm going to show you some of them in a minute. One thing that you can do with these events, by the way, this is propaganda, but you can use this IceCube R app in your phone to actually not only look at our alerts, but also look at them at 3 dimensions. You put them in so they can, it's an augmented reality system, so people can check this out, and we can talk about that later. So Um, the most probably relevant alert that we have seen or we have sent out was in 2017, and it was an event called 170922. So it was happening in September 2017, and it was an event that this is approximately horizontal. This is the top view of the detector. This is a horizontal view. Remember, time is color. And this is a quite high energy event, most likely neutrino energy, almost 300 TeVs. So this was sent as an alert to our peers, and people started looking into if this comes from a given source. Here is the, oops, what happened? Yeah. This is the actual event. Came from this direction. The direction of this event is actually quite well reconstructed, even if our even for our online system. And let me show you this again. So this is this 1702 1722 event. And this event actually was seen in coincidence with a flaring blazar, and the blazar was TXS, and Fermi saw it within 0.1 degrees. And so this actually was the first high significant astrophysical neutrino source. So I've shown things in a little off sequence. The NGC observation actually came later. This was actually earlier. So this was really exciting in our community. And it was seen in other observatories. For example, MAGIC also saw this flaring event. And I believe I have an animation. Hopefully this works. So this is how things went. So IceCube saw the event in September 2022. The weather observation was Swift, Fermi following days. Arguelles, MAGIC, SALT, and other observatories. And eventually this led to a campaign of observation of this event that led to publications in Science. Okay. So what we did is we brought this paper, which was multi-wavelength observations of the IceCube event. But then what we also did is look at IceCube archival data. So now that we knew that that event was most likely an astrophysical source, we went back to our data and said, like, is there anything weird happening in that region that we maybe did not see before? Okay. And this is the weird part. This is actually maybe, well, let's see if you think this is weird. I think it was weird when it happened, but maybe not anymore. So this is time, okay? And what you're seeing here is this is the time of the flare. Like, this is our event. Sorry, this is our event. And then this here is in yellow, the sort of excess of neutrinos as a function of background. Okay, so these are significant plots. So you can see is that, yes, there was a flare in the end of 2017, and this flare was very correlated, or was correlated with these high energy gamma rays. However, earlier, in 2015, there was a significantly larger flare of about almost 20 events that appeared earlier. But that flare actually had no gamma ray emission next to it. Okay? So why is that the case? So we're going back to this issue of what's going on in these sources. So one hypothesis is that maybe the gamma rays that were emitted together with that neutrino are actually getting trapped in that source, or somehow cascading down that source. And how can we understand this? Well, what we can understand this is think about the relative opacities between proton-photon interactions and photon-photons interactions. So the transparency, so how long a proton can go in a gamma ray bath, can be related to how much a gamma ray can go in the same gamma ray bath by the ratio of the relative cross-sections between P gamma and gamma gamma cross-sections. So this is astrophysics, because you need to know the densities and whatnot. But this here is particle physics. This we know very well, right? This is essentially the ratio of pions to electron masses to some power. And so that means that this number is actually larger than 1, which means that if you have a target that is thick enough so that the protons are actually interacting, making pions, that target is going to be so thick that the gamma rays are no longer going to be able to exit it. Okay? So the idea is that when you have an efficient neutrino producer, potentially that source is no longer a transparent gamma ray emitter. And this seems to be, at least in agreement with what we're seeing for the diffuse spectrum, where if you had that plot I was showing you earlier about the soft component that tends to overshoot the gamma rays. Okay, I didn't show this. And so this is, I think, a nice way of seeing it again. This is the neutrino flare, okay, here. And these are observations in optical, gamma, and radio. And so you can see here that in the 2017 flare, this is the 2017, this is the 2015 flare. 14 here. The gamma rays were seen in conscience. However, here, no gamma rays. But we see an increase in radio emission. So one thing that we are doing now, right, is the idea is that maybe we should look for places that are essentially anti-correlated with these gamma ray emissions as times where neutrinos could be emitted. Oops. And these are other interesting events. So this is Big Bird, which I showed you earlier, close to PKS. This is TXS, and this is another PKS, is another ice cube event. And you can see the blue line corresponds to the time of arrival of our neutrino events, and the data points here corresponds to gamma ray measurements in this plot from Fermi. This is MAGIC and Fermilat, and this is Fermilat. And you can see that the time of arrival of the neutrino actually seems to correspond to a decreasement in the gamma ray observations. So the gamma ray neutrino correlation, this very simple picture, you're producing protons, these pions, and they're just going through and decaying. Maybe not so simple. Another thing that you can see is in NGC 1068. NGC 1068 is relatively close, so you don't expect significant gamma ray opacity. This is the measurement of the flux as a function of energy. This is the flux measured for an NGC 1068 in neutrino. These are upper limits of gamma ray emission. Right? So you can see here that the neutrino flux is about 20 times larger than the gamma ray upper limits. Okay, so something is going on here. Cool. Okay, good. I have 20 minutes. Great. And that leads me to, I think, 2 more points. So yesterday, or maybe 2 days ago, I was talking about that one of the things that we have done lately is to improve our directional reconstruction by using machine learning algorithms. So here, I remind you of this plot that shows you the neutrino energy and the opening angle between true and reconstructed direction on average. And the blue lines is the machine learning algorithm using a convolutional neural network. And this standard means a likelihood-based reconstruction. And this is for cascades. And the important part is that the cascade resolution using these machine learning algorithms actually was significantly improved with respect to traditional reconstruction. And what is actually important about cascades that we can do with cascades in particular? So if you remember, cascades is something that we can use to observe the southern hemisphere, right? Because there are no muons, we can reject all of the downward-going muons. Which means that the cascade effective area is actually comparable, or sometimes larger, than the muon effective area in the southern hemisphere. And now, in this sort of resolution, we can get to order 3 or 5 degrees angular resolution. And that resolution is such that it starts to be comparable with the size of the galactic plane than we see, of the galactic plane. And so the idea is that, well, Naoko Kurayashi, who is a professor at Drexel University, had the idea of like, well, what about if we use this new machine learning algorithm and look for cascades and see if we can see the galactic plane in the southern hemisphere? And so people thought that didn't work because cascades don't point well, it's going to be terrible and whatnot. But it actually worked. This is embargo, so please don't share this. This is the observation of the galaxy in higher neutrinos. And so here, you can see that the galaxy has been observed in multiple messengers, optical, gamma. This is the pi zeros, if you extrapolate from these gamma rays. And if you compare these pi zeros to charged pions and assume that there is no opacity around them, then you can get that this should be the neutrino observation. And this is what we actually observe in our data. So we see actually excesses in the right places. And this has is going to appear in the press pretty soon. But I mean pretty soon, I mean order weeks. And this is actually a 5 sigma level statement of seeing the galaxy in neutrinos. And so the measurements of the galaxy, actually, well, 4.7, depends on the morphology of the galaxy. So for example, if you use this pi0 map that comes from Fermi, the significance is of 4.7 sigma. And so here what you can see is the measurement of the spectra of neutrinos from our galaxy. This is the neutrino energy. This is the flux. And you can see that this is the size of the all-sky diffuse emission. And this is our measurement, assuming this different model. Like this is the pi0 template of the spatial distribution of the neutrinos. So it's about like order 10% of the diffuse contribution. So this is likely the most, unless something happens in the next 6 months, but this is probably the most significant result in neutrino astrophysics this year. Last year being the discovery of NGC 1068 as a neutrino source, and this year being the observation of the galaxy in neutrinos. So it's pretty exciting. Okay, so now I'm going to stop because tomorrow I want to talk about neutrino oscillation and particle physics, and I have about 15 minutes. So I could do two things. I could take questions, or I could talk about oscillations for 15 minutes, and tomorrow I could do particle physics. So what do people want to do? Are there questions so far? People should be more excited, you know? We just found the galaxy in neutrinos. I think should be more excited. And questions? Yes, questions. Good.
So recently also tidal disruption events were associated with neutrinos.
Yeah.
And this neutrino signal was pretty delayed after the peak of the tidal disruption event in optical wavelength. So that's also kind of anti-correlation with just like gamma ray. So
Yeah. Yeah, I think you're right. I didn't talk about the tidal disruption events. That's true. I think those are less significant than these, 4 sigma level observations. But I think that's also very interesting. And I think that this is going to be the trick, right? I mean, understanding that relative delay, and not only the relative delay, but what wavelength of light actually is coming out. Because, if you could figure that puzzle out, you could do a very good like catalog search or whatnot, where you could actually correlate neutrinos with these sources, right? So this is the game we're playing right now, and I think that, broadly speaking, this picture I painted you is correct. But if I were to give this lecture in 10 years, probably the details will be 100% different. But this is what happens when you're working in an emerging field. So, yeah, thank you for bringing that up.
Can you back to slide 184, please? Oh, yeah. So just a quick question. I'd like to know where this radio data come from. Do you know?
This radio data, I think, comes from OBRO, which is the OBRO Observatory. It's in It's in the west of the U.S.
Okay.
I don't remember the exact acronym, but I could find that for you later.
Okay. Do you know if there is it is a interferometric radio telescope or?
No, I don't remember.
Okay.
Sorry.
No problem. Thank you.
Thank you.
More questions?
So the improvement in the direction of the neutrinos was very. I mean, this was order 1.
Mm-hmm.
So the fact that you're being able to see now the galaxy, which is really amazing, is it equally a matter of integration time and reconstruction, or it's mostly reconstruction? I mean, it's not such a big. I mean, it is an order 1 improvement. So it was impossible to see the galaxy before. Now it is. It's just reconstruction, or it's also just integration? What?
Yeah, it's mostly reconstruction because the background scales quadratically with the resolution. So the much background you're integrating is quadratic with the opening angle. So an improvement of order 1 is significant reduction of background. And it's not only an improvement in error, but in reduction of bias as well. So yes, I would say like it's essentially entirely systematically riveted. Let me say this in another way. We look at NGC 1068 with traditional reconstruction before, that was, somewhere around the 3 sigma level. And with the improved machine learning, with essentially the same data sets, we almost go to 5 sigma. So it's an improvement that's essentially reconstruction dominated, which is great, because that means that, if we figure out to make this reconstruction even better, that's opportunity for further discoveries.
So continuing this topic of the galaxy, so before you talked about the sources that are optically thick to gamma rays, right? Could you expect something for the galaxy? Are there regions in the galaxy that would be optically thick for photons that you could look for anti-correlation between neutrino and photon?
Yeah, so my understanding is that what we're seeing here is cosmic rays hitting gas in the galaxy, so it's the emission from gas. There is also sources that emit gammas in our galaxies. Those are unresolved sources. Those sources could have opacity in those environments. My understanding is that at least in the production in the overall gas in the galaxy is not that dense enough for it to be gamma opaque. So when you're seeing this, well, this is just coming from Monte Carlo, assuming just gas, but the data, it has to be a combination of the gas emission and also individual sources that are unresolved yet, and those could have dark gamma components. This is a question that we will know in some years.
I have one question. Can be that this delay between the neutrino and the gamma part is that the beam, you see neutrinos not from the main direction of the beam, but from 90 degrees. For example, the beam is like the news coming from one direction and photons coming from the other direction, and then because the photons need to cross a lot of part of the what is the source is.
Yeah, so I mean, gamma rays at this sort of like relatively low energies, TVs, to be transparent in our galactic scales.
Okay.
So we shouldn't expect that opacity to happen. The galaxy, PV gamma rays essentially are attenuated in our galactic scale, but these other TV gamma rays should be mostly transparent. And I think the assumption in these calculations is that the cosmic rays are totally diffusive in nature, so they're going in all random directions. But these are very boosted particles, so that I assume that the neutrinos and the gammas are very correlated. Well, I guess we're not exactly talking about the same pion, right? Oh, great. That's a great question. Thank you. One of my students working on that. So what Orlando is asking is, when you have cosmic rays hitting the sun atmosphere, can we see those? The answer is, I hope yes. We are within a factor of 2 of seeing those with our latest sensitivity. And we hope to blend that analysis this summer. And so maybe we'll see them. We're between rolling a dice of seeing those neutrinos, I think. And I will talk about that a little bit tomorrow.
Questions? Comments?
I guess that will be the discovery for next year.
Hopes?
Okay, I think that since we have about 6 minutes, it's not going to be enough time to talk about oscillations. So we'll talk about oscillations tomorrow and particle physics results. And,
Okay.
thank you for your
Let's
time.
thank the speaker.